Hello, everyone, and welcome to my brown bag about intelligent agents. My name is David Kuboň, and I will be presenting it. When I was asked to do a brown bag on artificial intelligence, some part of it, I wanted to pick a part of AI that has not been covered during our machine learning lunches and is not entirely boring, like anything with a lot of statistics in it. I picked intelligent agents because they're seen throughout AI, and I hope I succeeded. So when you tell people you are doing AI, they mostly imagine robots. Some of them have also heard about neural networks or about machine learning in general. But often these topics are not clearly defined to them, and they don't really realize the interaction. So what is the difference between AI and machine learning and neural networks and all the things you might be hearing about here in Salsita? So artificial intelligence, which is what I will be talking about here in this brown bag, is basically any technique that enables computers to act like humans. While machine learning, which is a subset of AI, uses statistical methods to perform like humans do. And deep learning is a subset of machine learning, and it works with multi-layer neural networks. It is also what we are using on some of our internal projects. Generally speaking, there are 4 main views into AI based on the main focuses. So we can look at performance, either from the human or ideal perspective. We can examine the thought process, and we can look at the behavior. So if we want to think humanly or think rationally, those are things not that much covered by AI, like psychology, neuroscience, and logic, which is mostly mathematics. But if we look at behavior, that's the cool AI part, where acting rationally, and note that this is ideal and not human performance, because humans are definitely not acting rationally, as someone also pointed out in some previous brown bags, like Dani Lopez. And the behavior could be like acting like humans. And an example of that is a Turing test. So what is a Turing test? It's a hypothetical scenario where a person, an interrogator, is presented with a conversational partner. And this said partner can be either a computer or another person. And the interrogator is supposed to distinguish whether he is talking to a person or a computer. While this has not really that much of a practical use, we keep encountering the reverse Turing test in our everyday lives. That is when a computer is trying to figure out whether you are a computer or a human. So whenever you need to select all the images with a zebra crossing on them, or a car, or I don't know which ones are used at the moment, or you need to write some random bunch of letters and numbers, that's when you are being reverse Turing tested. Before we move any further, let me ask you this. Do you, here, the audience, think you ever wrote any AI? Some people are nodding, some people are ignoring me. Well, you certainly did, because a simple decision tree, which is basically an if-then-else clause, is an AI. This one in particular helps new Salsititas pick where to go for lunch. Decision trees are one of the simplest form of AI. They're clearly white box. You can see how their decision was made. They're super easy to interpret because you just read through them. They can handle both numerical and categorical data. I did only categorical one here. They require a little preparation. It was like 5 minutes. And they pretty much mirror human decision making. On the other hand, they can be pretty non-robust. Finding an optimal one from data is NP-complete. And often they can be too complex and generalize badly. you can create them manually, or you can try to learn them from your data. And one of the advantages there is that you don't really need to pre-process the data much, because you can use pretty much anything. So what about those intelligent agents I'm supposed to be talking about? An agent is some entity that lives in an environment and perceives the environment, and using some actions, it affects the environment. So imagine it is a lovely day on the planet of Tatooine. The two suns are glowing over the horizon. It's really hot. It's really dry. You used a lot of sunscreen, unless you're an agent or a robot, then you didn't. And your friends are about to be eaten by this lovely monster. So you are perceiving the environment and waiting for a signal. And once you see it, you shoot out a lightsaber and everyone is saved. I didn't find any nice gift for that, so you won't see it. So that was like the basic example of an agent behavior. The agent was perceiving the environment changed, the agent noticed and performed an action it was designed to do under such circumstances. But it's not just movies. We meet intelligent agents during our daily lives. Some of them are much simpler. Some of them are pretty complex. So how can we tell whether an agent is doing its job properly? We need some sort of a performance measure to tell that. And so in this example, if we say, okay, the measure is how much coffee it can make, then the filter machine and the espresso machines are really good agents. We could theoretically use the Mac to order some coffee online, so that's not too bad, right? And we could use the Tesla to drive somewhere and fetch some coffee. So only the headphones are terrible. But still, it's not a very good performance measure, right? In human world, money could be considered a performance measure, but it's not a really good one either. Because A, it doesn't show if you've actually performed well or if you just received a lot of money for it. And B, same amount of money could mean very different things to different people. If you're rich, $1,000 means nothing to you. If you're poor, it could be a lot. What does that tell us? That tells us that the performance measure needs to be very much task-dependent and very specific. Let's focus on the Tesla, because there are a couple smaller agents within the bigger agent. If we start from the simplest, there are the headlights, which are automatic. And so you're driving in daylight, and you enter a tunnel. And they turn on automatically, because the simple agent perceived a change in the condition it was supposed to observe, and performed the action it was supposed to do at that time. What about the volume? You wouldn't like it if it behaved the same way, because then you could do only silent and loud. So you wanted to have some intermediate steps. So you need the agent to perceive whether you press the plus and minus buttons, but you also needed to know what state it was in before and move just one step. Okay, something more complicated, navigation. Navigation is a goal-based agent. So what that means is that it can sort of prepare a set of actions for it to reach a specific goal. The thing is, it can only tell whether it successfully reached the goal or not. It's lacking any measure to evaluate the intermediate steps. So basically, you're driving and you're following the path. If you do that and you reach the goal, you've succeeded. But if you take a wrong turn somewhere, and the set of actions in that case is that like turn left, keep straight, on the roundabout, take second to the right. And if you keep doing that, you will reach the goal. If you don't keep doing that, you're basically resetting the navigation to do the navigation from the new point that you got yourself into to the initial goal again, but it's a new task. So it didn't succeed. And if we look at the car itself, it's the most complex type of agent, a utility-based agent. It basically describes some performance. The utility describes the performance measure of the whole thing. And it can have conflicting goals. It can have multiple goals. It can evaluate how well it is performing on the path to the goal. So for instance, it could consider when heading to the destination how far you are. It can choose the quickest route, avoid road closures, traffic jams, ensure the safety of passengers, and all that contributes to the utility of it. Of course, all these agents can also learn. For that, they need to be given some tasks. They need to be able to evaluate how well they performed on them and have some mechanism to improve the program they're running and make it better next time. I will focus a little more on the goal-based agent, the navigation task. So we have the problem set up. We are starting in Salsita, and our Tesla needs its annual check. So we need to drive to Vysočany, to the Tesla service point. So we have a start state. We have a goal state. We need to be able to test the goal state. So like ask, are we there yet? When we get to the point, the answer will be yes. Or like the car, like for real, we'll just check the GPS or something. And we are also considering the cost of the path, either in time or money or whatever suits us. A task like this would be really difficult to accomplish because there are so many unimportant things affecting it. So we need to do some abstraction. We need to remove unnecessary states. So for example, if we are driving, we don't really care about the weather, the day of the week, the color of the car that was parked next to us when we started. And we also don't care about unnecessary actions for the sake of the navigation. So we don't care whether we will turn on music or not, or turn off the AC or whatever. With these conditions, the agent will search, and search is like the core of AI for many tasks. It will perform either blind or informed search. In case of blind, it's some depth first search, iterative deepening. We can search from both ends of our path and try to meet somewhere in the middle. We can do various things. Or an informed search where we have some heuristics to help us get to our goal easier. I will talk about one particular algorithm, which is, with its some modifications, is somewhat commonly used, despite it being pretty simple, and that one is called A*. So A* basically adds heuristics to Dijkstra's algorithm for path finding. The path to some node n is the path we needed to take up to that point from our initial state, plus some heuristic estimate of the rest of the path. It is essential that this heuristic estimate is better than the possible true values, and that it doesn't get like better during the computation, that we can only get worse. So in terms of navigation, the path so far will be the true distance we already traveled. And the estimate could be, for example, the like straight line from whatever point we're at the moment to our goal. Or if we are walking, it could be how much time it takes on a bicycle or something. That's not a really good heuristic measure, but just to give you another example. And how does the algorithm go? Basically, at each step, it will evaluate or explore the node with the lowest path to node value. I'll show you a specific example. So we are at Salsita. We want to get to the Tesla service center. The black values are the true cost on that path, let's say kilometers. And the gray values at the nodes are the heuristic estimates from that node to our goal. So in the beginning, the path through A is 5.5, and the path through D is 6.5. So we move to A, and we continue. So the path through B is 5.5, and the path through D is still 6.5. So the path through B is still better, so we just continue through there. And now the path continuing to C is 10.5, while the path going to D is 6.5. So we give up on this branch of the search, and we start exploring the path through D. And so on until we reach the end. Okay, this was one usage of agents, a goal-based agent. And now let's go for some other, maybe even more exciting usage of intelligent agents, games. So we will focus on turn-based, deterministic games with perfect information. That means that the opponents, the agent and its opponent, or multiple opponents, will take turns playing. There's no luck, no randomness in the game whatsoever. And all the players can see everything. So there's no hidden cards, nothing like that. Some examples of such games would be chess, checkers, tic-tac-toe, and so on. The principle used to play such games is adversarial search. So you're searching, knowing that someone will try to make it hard for you. And the algorithm in particular is called minimax. It might sound simple, but it's still used with great success. So as you can see, we have a complete tree of the game. So it covers all the possible scenarios that are legal within the rules of the game. We have the initial state of the empty board in this case, the legal moves, and the leaves represent final positions, positions in which we can tell which of the players won or whether it was a draw. If we explore the whole tree, optimal strategy will always be found, but that might take pretty long time. So I will just explain the algorithm a little more, and then I'll get back to how long that might take. Here we have the agent playing, and the opponent playing, and the agent playing again. In the leaves, we mark the victories of the opponent with -1 and red, and the victorious games of the agent in blue and +1, while draw is black and 0. So why is it called minimax? Because the agent in its turns tries to pick the subtree, and I mean, each step represents a particular move, here placing the X here, placing the X to the top right corner, and so on. So the agent tries to pick a subtree in which it has the highest chance of winning. So basically, the most leaves leads to his victory, and the least leaves lead to the opponent winning. So based on that, the agent will pick the middle subtree. Because in the left one, it's -1 and 1. In the right one, it's -1 and 0. And the middle one is 0 and 1. So it's clearly better. But now it's the opponent's turn. And the opponent is trying to minimize the chance of the agent winning. So what it does, it picks the subtree with the lowest value. So in this case, it will play the O here to the middle of the top row, because in that scenario, the agent will have no choice but to draw. So this is clearly a lower value than this one, and that's why it will happen. Okay, so back to tic-tac-toe and the computational complexity of this. So in tic-tac-toe, there's 255,000 possible games, legal games. Games meaning a path through the computation tree, leading to a different leaf. If we consider some rotations and reflections of the board, because we can essentially do that, we are down to 26,000. That's computable, but might be taking a little too long. So what can we do? We can use something called alpha-beta pruning, where we basically stop the evaluation when the minimax value of the child is worse than the parent. So for example, here, the opponent will try to minimize our chance to win. So it will never play the move, which would result in an 8, 8 being like higher value than 5, so it will always pick 5. So there's no reason to explore this subtree. Okay, so tic-tac-toe, 26,000, and some pruning. That's pretty easy, right? We should win. Okay, so what about chess? In chess, there are 200,000 possible games after 2 turns. Okay, so there are 121 million games possible after 3 turns. Overall, it's not doing what it should. Okay, overall, it is estimated to be a lot more than the multiplication of the total of human hairs times the grains of sand on Earth times the number of atoms in the universe, which is approximately 10 to the 119. And it's still a lot more than that. No one knows the exact number. So this might be a little difficult even with some alpha-beta pruning, right? So what can we do? Obviously, we are not able to go down all the way to the leaves to figure out the true value and then prune it. So we need to do only a couple of turns ahead and use some heuristics to evaluate the position. A basic one in chess could be the sum of the value of the chess pieces. That works to some degree. Only the agent is not really willing to sacrifice pieces in order to gain a better position. And still, there's an issue, because what if we capture the queen in the next turn? Then the value of the pieces will change significantly. So how this is solved is that whenever there's something like groundbreaking about to happen on the board, a couple more turns are played, like a couple more levels of the tree are explored before the heuristic evaluation is done. All right, so let me introduce Stockfish. It's one of the best 2 non-neural network chess engines. I think they started in 2008. And they won the championship like 6 times and finished second like 5 times. How does it work? It works exactly like I said. It uses minimax with alpha-beta pruning and some a little more sophisticated human-like heuristics. So for example, it considers the structure of the pawns on the board. It considers the value of the material, considers how far into the game the players are, how safe the king is, and a couple other things, and evaluates that and gives the move. Okay, so this one was pretty good and beat humans consistently. But then in 2017, it lost to AlphaZero, 467 to 733. And AlphaZero is also a minimax. But the only difference is that it uses neural networks to evaluate the positions. And if you know how to play chess and you didn't do it so far, check some games, because it's really interesting how it plays. Okay, so chess, humans are beaten pretty consistently. The computer's beating, humans are beaten. So what's next? What about Go? The difficulty depends on the size of the board, obviously. Beginner boards are 9 by 9 or 13 by 13. And already for the 9 by 9 board, there are 10 to the power of 37 legal positions at which the game might end, but a lot more possible games how to get there. Full board is 19 by 19. I'm not really even bothering to read that number, it's just too huge. And the number of positions on the board that were achieved legally was only discovered 4 years ago, because before that they just didn't manage to compute it. And the number of possible games depends on their length. For 200 moves, which seems to be the standard on this board, it is about 2 times 10 to the power of 481. All right, so before neural networks came to play, humans were far better. Computers could occasionally win on a 9 by 9 board against pros, or on a 19 by 19 board against amateurs. I mean amateurs, not noobs. In 2015, Elon Musk claimed that it will take a minimum of 10 years for a computer to win against a pro on the full-size board. But next year, the 18-time world champion from South Korea lost to a computer 1-4. That computer, again, was a simple minimax using heuristics to evaluate the position. And the heuristics were based on neural networks. By the way, as a complete side note, I saw Elon Musk's Starlink satellites last weekend, and it was really cool. I do recommend you to have a look. There's an app, you can find where it is, get up at night and check it. It's really cool. Okay, so what's the message to take home from this presentation? The main message is that we skipped a lot. Even in terms of agents, there's constraint satisfaction, there's planning of the actions, there's scheduling, there's some uncertainty within the environment. We didn't consider time. We ignored completely most of machine learning, neural networks, deep learning, all that. So maybe another brown bag by someone else next time. And thank you for your attention. If you have any question, now's a good time. Looks like no questions here in the club.
Looks like no questions.
Okay, thank you.